So picking up from where we left off, we were talking about atoms, and this is what is called the Bohr model of the atom. The Bohr model of the atom maintains that the center of the atom is a nucleus, and then surrounding the nucleus are these circular energy levels. This is an older book, but it's kind of easier to see, I think, how this works. So this is what Bohr thought the model of the atom looked like. I don't know if any of you back in junior high or anything built models of atoms that were like Bohr models, where you had something in the center and then some wire things around. Any hands up? Any of you do any of that? And you put like little, oh, I don't know, cotton balls or something to represent the electrons. Is that familiar? Yes. Fun to do, total junk. Okay, totally wrong, but it's a cute project anyway. Because atoms aren't really like this, but it's a good model. Bohr thought that this model was accurate because, based on what he's designed here and some calculations that you'll see next semester, this model works beautifully for hydrogen, but it doesn't work at all for any other elements. It works for anything with one electron. So hydrogen, helium plus 1 would have 1 electron. Lithium plus 2 would have 1 electron. Anything that has only 1 electron, this model works mathematically, but it doesn't really work in the real world. Okay, so what we have to do is reevaluate our models. However, we are still going to see the truth of the model in that there is something to it, in that, in fact, what you get are very discrete bands of energy when you look at the spectrum. So there is something to be said for energy levels. There are energy levels. That is true, but they're not these perfectly round circular orbits that we think there are. Okay, they're a little bit more complicated than that. And electrons do, in fact, jump from lower shells to higher ones when they absorb energy. That's called excitation. And when the electrons go back to their home shell, that is called emission, or they emit a photon of light. And that photon of light is what you're seeing in the spectrum. Okay, so we're still kind of talking about matter and light, the atom and light, because there's a lot of important relationships between them that we have to focus on. So what is light really? You know, if we look at light, what is it really? We've already kind of said we can describe it in two ways. We've said it's particles called photons, and it's waves. And it's both things at the same time. It's really beyond, I think, our brains to be able to digest. You know, trying to imagine it is really hard. Now, even though the Bohr model isn't entirely accurate, there's one aspect of it that is. And that is, electrons are only able to go to discrete energy levels. In other words, the electron can be on energy level 1, 2, 3, 4, but it can't be, there is no level 3.5. There is no 9 3/4 or anything like that. There's only level 1, level 2, level 3, level 4. And if the electrons are at one point, the atom has a certain energy. And if the electrons are at another level, the atom has another energy. But what we say there is that the energy is quantized. What that means is there are only specific allowed values of energy for the atom. Okay? There's not an infinite number of ways that things can be there. So, as an example, and the book gives a good example here, a good analogy. The book talks here about this kind of as like a ladder. So electrons can be at the first level, the second level, or the third level. There are only so many levels. They can't be at all in between. It's also kind of like, I think, if you look at it like a ramp. if we look at a ramp, if I was to do this real quick, and I were to put a ball on the ramp, this isn't going to cooperate with me. All right, I'll have to do it the old-fashioned way. Try to draw a ball. Just don't want the ball here. Not too bad. How many different places on the ramp can the ball be? Technically, if you think about it. How many different places can the ball be? It could be at the top, at the bottom, halfway, and then between the top and here it could be halfway, and then between the top and there it could be halfway. In other words, am I ever going to run out of ways of positioning that ball?
No.
No. Now, there's an infinite number of places that ball could be, right? Because every time you cut this in half, you could always find an infinite number of places. So what we say about this kind of a thing is that with a ramp, we say that the energy is continuous. It's like numbers. If you look at it's like a number line. If you look at 0 and 1, how many numbers are there between just 0 and 1? There are infinite. Yeah, it's infinite, right? Because you can go between 0 and 1, there's 0.5, 2, 5, and then you can keep dividing in half forever and ever and ever, and you'd never run out. Okay. But on the other hand, with what we're saying about atoms and their energy, it's much more like, and these are supposed to be perfect, straight. They're not supposed to be bent. They're kind of like stairs. Where the idea is the ball can be here, and if it's perfectly flat, so that's one energy, or it can be here, or here, and it gets flat, or it can be here. And so there's only levels allowed. That's what we call quantized. In the real world, what are most of our things? Are they continuous or quantized? Like the speed on your car. If you really get down to it, are there only certain speeds on a car, or are there technically infinitely many?
Certain speeds.
Many?
Yeah, there's infinitely many. Because, you know, just between, say, 0 and 50, there's 25, then there's 25.1, 25.01, 25.001. And, you know, in theory, you know, if you have a radar gun that's measuring your speed, depending on how accurate that gets or how precise, you can go out to the thousandths place, the hundredths, thousandths place. I don't know that we have the technology to do that. But there's an infinite number of speeds that you could technically be going. Now, in terms of what your odometer says, your odometer is only going to say 0, 1, 2, 3 miles an hour. But in reality, there's speeds in between all of those. So, yeah, you have infinitely many speeds that you could be going at. So that's not what we're used to. We're used to a more continuous level. Okay. Whereas this is called quantum or discrete. Any of you had statistics?
I had statistics.
Yeah, when you take statistics, one of the first things you talk about are probability distributions, right? And you talk about things that are continuous, and then you talk about like binomial distributions or Bernoulli distributions. Does that sound at all familiar?
Yes, it does.
Yeah, and geometric distributions, those are all discrete. Like, you know, if you're flipping a coin 10 times, if you count the number of results that you can get, there's only a certain number of results. So there's only certain probabilities you can get. On the other hand, things that are normally distributed were continuous. If you study the normal distribution like a bell curve, because you can always go into, like if you're measuring people's heights, you get always half of their heights and half of that and half. So there's an infinite number of values that you can technically have or to measure them. We're not going to ever see someone that's 12 feet tall, but a normal distribution allows for it. It says, hey, it's possible. So those are all theoretical possibilities. All right, now I think I've overbeaten this point, but it is really an exciting point because it allows us to understand what's going on. And that's really what quantum mechanics is at its heart. It's just saying there's only certain values allowed. Okay. Now, although we're not going to really focus on it in this year, you'll focus on it in Chem 130 a little bit more. You can technically also describe matter as being like waves. So an electron is a particle, but it's also like a wave in some respects. Okay. Now, look at your hand. Is your hand waving? Are you seeing your hand blink in and out, wave or anything? No. Anything that's macroscopic like us, or a car, or a baseball, those things, the wave part of it is insignificant. It's so small that it doesn't matter at all. But when you get down to the very small things like nuclei and electrons, they are also a little bit like waves. They have wave-like particles, which means in theory, they kind of, I don't want to say that they blink in and out of existence, so to speak, but because they're like waves, they can have positive amplitudes, negative amplitudes, they go up, they go down in their own little way. So ultimately, what this means is, instead of saying that things are at a definite position, we have to say we think an electron is here. It could be there, it could be there, but we can't say for sure. There's always some uncertainty. You'll learn about that. It's called the Heisenberg uncertainty principle. Okay. All right, so we're going to move from the Bohr model of the atom to the quantum mechanical model right now, which is a little bit more accurate, or not a little bit more, it's much more accurate. Okay, so electrons don't go around the nucleus in a circle. Electrons, however, are contained in space, in regions of space called orbitals. And these don't actually exist. There's not actually, going to be these things, but they're basically plots of space where we can say, I think the electron's going to be here. It's like a border, okay? A border is a concept we see. We know that there's a border between here, this state, and this state, right? It's not usually marked or anything all the way there, but we know it kind of exists, so to speak. So an orbital is kind of like a border region that says, this is where you're probably going to find the electron, is inside this orbital. Within each shell, we get a set of these orbitals, and we call those subshells. Okay, so now keep these three terms in mind. Shells. Shells are the same thing as these energy levels. So I could call this shell 1, shell 2, shell 3. Or I could call it energy level 1, 2, 3. So shell, energy level mean the same thing. A subshell is a collection of one or more orbitals. Okay? Regions of space where you can find the electrons. And the orbitals are themselves those regions. The orbital types that we deal with for all existing atoms have the types S, P, D, and F. And for any given energy level, that's their order in terms of lowest energy to highest energies we're going to see. Very, very important here. An orbital that region in space can hold up to 2 electrons. So that means there's 3 possibilities. An orbital is empty, an orbital has 1 electron, an orbital has 2 electrons. And that's it. Can't have anything more than that. So it's probably good to think of orbitals like rooms, you know, or hotel rooms, the way I like to do it. It's an empty room. It's a room with 1 person, but it's got 2 beds in it. So 1 person in one of the beds, or it's got 2 people in the 2 different beds. No sharing beds here. Not allowed. Okay. So it's kind of good as a mental model to think of the shells as being divided into subshells. This is not a very good picture of showing what orbitals look like at all, but it's just telling us effectively how this works. So you'll notice on the first shell, you have one kind of a subshell called S. We call that the 1s subshell. On the second shell, you have a 2s subshell and a 2p subshell. On the third, you have 3s, 3p, and 3d. And then from 4 on out, you have 4s, 4p, 4d, 4f. So we're going to look at these now in more detail. Okay. So an orbital, an s orbital, least energetic for the electrons that are in there. And it's always shaped like a sphere. And every energy level, as we saw, has one s subshell. And that s subshell contains exactly one s orbital. Okay, so what is an orbital if we're trying to look at it? Now, it's not really possible to do this, but what I want you to imagine is we have a nucleus right here in the middle of this thing. And imagine we took pictures of the electrons, the one electron at many different times. So it's like we're taking pictures over and over and over and over and over of where the electron is. And you agree, it looks like the electron is forming kind of a, this is 3-dimensional, so it would be a sphere. So the electrons are staying mostly within a sphere, it looks like. So using that, using the previous picture, we go ahead and say this is what an s orbital is. Okay, it is a spherical region. Now putting those two on top of each other, are the electrons always inside the orbital?
No.
No. So what do we say about the orbital? It's where the electrons probably are. Okay? It's where they are most of the time, most likely. And theoretically, these electrons could be over here. They could be over there. They could be in Oregon. You know, quantum mechanics admits all those possibilities. But what we say is it's a region of space where you're most likely to find it. Again, does this thing really exist? No, this thing doesn't really exist. It's just trying to show us where in space the electrons are. So how many electrons can we get into this thing? It's an orbital, so you can get up to 2 electrons, and that's it. So imagine again, this is a picture of just 1 electron in all its different points of time. If there's 2, it would look the same. You know, we'd see the 2 different electrons taking these different spaces. Okay. So on the first shell, you have a 1s orbital. On the second shell, you have a 2s orbital. You'll notice the only real difference is, from what you can tell, is size, correct? So the 2s orbital means the electrons can spend their time even farther away from the nucleus. The nucleus is right there in the middle at the origin. And the 3s is even larger still, but it's always spherical shaped, and every energy level only contains 1 of these that can hold 2 electrons. Starting with the second energy level, and going back to my picture here, you get what is called a p subshell. And a p subshell contains p orbitals. S subshells only come in sets of 1 orbital each. But P's always come in sets of 3 orbitals each. Okay? So whenever we say the P subshell, the 2P subshell, or the 3P subshell, or the 4P subshell, there are always 3 orbitals in that subshell. So it's like 3 bedrooms, okay, with 2 beds in it. So you can hold up to 6 electrons, right? Again, my hotel room analogy, each bedroom has 2 beds. You have 3 rooms on a certain level. So that means you can get up to 6 people in there. They are not spherical. They look kind of like teardrops that are attached at their tips. So this is one of them. So kind of looks like a teardrop here. And then another teardrop attached to it here. This whole thing is a p orbital. So we don't say this is a p orbital and this is a p orbital. No, this whole thing is a p orbital. Okay. And again, it's just like a border. It's where we're likely to find the electron. It can be here or here with equal probability. We can hold up to 2 electrons in this space. We don't need to worry about the names of all of them, but we call one of them py because it's on the y-axis. And as you might guess, there's going to be one that's on the z-axis and one on the x-axis. That's why there's 3 of them. What's at the middle again right here?
The nucleus?
The nucleus, good. And you see this blue plane right here?
Yeah.
That's a really interesting thing. That is called a node. That is a region where the electron cannot exist. So the electrons cannot exist there. But what is fascinating about that is the electrons can be here, and they can be here, but they can never be in between. Okay? Which is, again, a real big difference between what we're used to in the real world and what we see in quantum mechanics. You agree to go from one room to another, you have to go through a doorway. As human beings, we have to. Electrons don't encounter that problem. Because they're waves, it's just like as waves, they just come to a wavelength of like about 0 at that point. Or not wavelength, an amplitude of 0. So it's almost like they blink out of existence, and then they cross over. So, and this is happening, incredible numbers of times in a second. So, yeah, they can do that, but they just can't be right there on that plane. Okay, here's another picture of one. This is on, we've drawn it differently here, so this is now the z-axis. So, again, showing you where the electrons can be found. So a subshell, remember, is a set of all the orbitals together. So since p's come in sets of 3, this is going to be 3 orbitals. The one on the x-axis, the one on the y-axis, and the one on the z-axis. I'm not sure if everyone has dealt with z-axis yet, but it's the same concept as your x-y axis or your Cartesian coordinate, except in being in 2 dimensions, we now open up a 3rd dimension. It's like being above the paper and below the paper. That's what the z-axis is telling you here. How many electrons again? We can get up to 2 in here, up to 2 in here, and up to 2 in here. So a total of how many electrons can fill this subshell?
6.
6, yeah. So later on when we get to electron configurations, you're going to remember P has a maximum of 6. S, on the other hand, had a maximum of, it only comes as 1 sphere. This can only hold 2 electrons, and that's it. So let's think about this then. How many electrons can be in the first shell? It only has 1 s orbital in it, so how many electrons?
2.
2. How about in the second shell, how many electrons?
4.
The s can hold how many?
2.
2, and the p can hold?
2.
Remember, but there's 3 of them.
6.
6, right? Because there's 3 p orbitals. So 2 plus 6, you can hold
8.
8. Yeah, good. Now, when we get to the next sets, the pattern continues of odd numbers. So S's come in one S orbital, exactly one S orbital in a subshell. 3 for P's. D's have 5, and then F's are going to have 7 orbitals in them. And the shapes get ever more complicated. So how many electrons can we get into the d orbitals? If there's 5 of them, each orbital can hold 2. That means we can get up to
10.
10 electrons. And then the f orbitals you can get up to
14.
14. Good. Let's take a look at the pictures of those. And their pictures start to get really crazy. So these are the 3D orbitals. So they kind of look like the the p orbitals split. So, and you don't need to know the names of any of these. You just need to know that there's 5 of them. Okay. So we've got this one that's basically on the YZ plane. We've got one that's on the XY plane, one that's on the XZ plane, one that's also on the XY plane, but it's right on the axes. And then one that's totally different. It has what looks like a p orbital surrounded by a donut. Okay, and again, these are all regions where the electron is allowed to be. So it can be in here, it can be in here, it can technically be elsewhere as well, but this is where you're likely to find the electron. F subshells get even more complicated looking, so we're not going to look at pictures of all the F's. This is just one of the possible F orbitals. There's another one that looks like this, but has 2 donuts on it. And these all come from very complicated math. Okay, there's mathematical equations that tell us what the shapes of all these things are. Right. So just to summarize, because I think it's helpful to do this, I'm going to stick a piece of paper in here. Oh, don't need to go all the way back. It's really annoying. So let's just summarize what we've seen. Okay. So let's start off with energy levels. It's going to be a table. Also called shell. Shell 1. Let's say subshells. Say number of orbitals. And let's say number of, the max number of electrons. The maximum number of electrons. Okay, so the first shell contains a single S subshell, and we call it 1s. An S subshell always has 1 orbital in it. And so that's 2 electrons total. The second shell has a 2s subshell and a 2p subshell. S's always come in sets of one orbital. And P's always come in sets of 3. We can have 2 electrons in the 2s subshell, and we can have 6 electrons here for a total of 8 electrons in 2. And then we're full. We can't have any more electrons. It's like floors on a hotel. So now you have to go to the 3rd floor. When we get to the 3rd, there is 3s. There's 3p. And now we add a d subshell. Number of orbitals. S's come in sets of 1. D's come in sets of 3. D's come in sets of 5. And we can hold 2 electrons per orbital, so there'd be 2 in the s, 6 in the p, and 10 in the d, for a total of 18. And then we get to the 4th. We have 4s, 4p, 4d. And now we add that 4n. So we can have 1 orbital in the s. D's always come in sets of 3. D's always come in sets of 5. F's always come in sets of 7. And we get double those. So 2 electrons in the 4s subshell, 6, 14, for a total of 18 plus 14 would be what, 32? 32 electrons. Yeah, in the 4th shell. And 5, 6, etc. are similar. Now, technically, starting on the 5th level, there would be a 5s, 5p, 5d, 5f, and then we would add a g orbital. But no atoms that we know that exist have g orbitals. We just don't know any atoms that have those. It's a theoretical idea. So maybe for an excited atom. Starting with the 6th level, you also add h orbitals. But again, there's no atom that we know where we can show this to be the case. It's a theoretical concept at that point. We don't have enough atoms, known elements, to be able to demonstrate that. So for all purposes that we're going to worry about, it just repeats itself: 5s, 5p, 5d, 5f, and we'll forget about the other orbitals that we don't know about. So any questions about this? Okay, one more time. Definitions. Orbitals are regions of space where you're most likely to find an electron. Subshells are collections of those orbitals. S subshells are always a collection of one orbital. So an S subshell is an orbital. A P subshell, though, is a collection of 3 orbitals. It's called Px, Py, Pz. D subshells are a collection of 5 orbitals, 5 regions of space. And Fs are a collection of 7. What's the difference as you get larger and larger in the shells? As you get larger and larger in the shells, the electrons can start doing what? They can start moving further and further away from the nucleus. So what that means is an electron that's in 4s is much more likely to be far away from the nucleus than an electron in 1s or 2s or 3s. Just means the boundaries get bigger and the electrons can go farther away. These things all exist on top of each other. Okay? As I said, it's kind of a tough concept mentally. Now, to what we're going to need to be able to do, because we'll need this to be able to describe other aspects of atoms. We want to be able to come up with an address book for each atom that tells us where all the electrons are located. We want to know the address of all electrons. So in other words, we want to be able to say, if I go back to my sheet here, how many electrons are in 1s, how many electrons are in 2s, how many electrons are in 2p. I want to say where the electrons are going, okay? And ultimately, it says which subshells have electrons in them. And usually, you only list the subshells that have electrons in them. So for example, boron. Boron. If we look at it on the periodic table, boron has, let me go back here, so I'm on page 45. Boron has 5 protons and 5 electrons, correct? 5 protons and 5 electrons. So it's going to the first 2 electrons go into the 1s subshell. And then that's full. So this is the subshell, and then as an exponent, we list the number of electrons in that subshell. So then we move on to the next subshell, 2s. And we put 2 electrons in it. And now it's full. We still have 1 more electron to worry about, and so it goes into the 2p. It goes into one of the orbitals in the 2p subshell. Okay. And now we've run out of electrons. So this is the electron configuration for boron. 1s, 2s, 2p, sorry, 1s2, 2s2, 2p1. Notice there are no commas, okay, no spaces. The numbers are above, not below. So it's really important that you get used to writing them the correct way too. I'm a stickler on the way I want you to write them, so just kind of like I did here. Okay. Atoms always go lowest energy to highest energy when they fill the electrons. So this is called the Aufbau Principle. And German, Aufbau is German for building up. Okay. I honestly thought for years and years it was named after a man named Aufbau, because all these other rules are named after some guy or another. Okay. But Aufbau, it turns out, is a made-up word, building up. That's the cool thing about German, by the way. If the word doesn't exist, you can make it up by stringing together a whole bunch of other words. Whether someone recognizes your word or not is another thing. That's kind of how they do it. They just compound all these words together. Anyway. And now the order in which you fill the electrons comes from the periodic table. It is not, unfortunately, this order. You might think it's 1s, then 2s, then 2p, then 3s, then 3p, then 3d, then 4s, then 4p. It's not that order. It's a little bit more complicated, unfortunately. But we can use the periodic table to tell us the order. Rotate this page clockwise. Almost sent me back. Frustrating. There we are. Okay, can you kind of see how that looks like the periodic table? This tells you the order that you fill the electrons. Fill the 1s's first, then the 2 S's, the 2 P's, the 3 S's, the 3 P's. And then you skip. Instead of going from the 3 P's to the 3 D's, you go to the 4 S's. Now, this really kind of ingenious thing shows us that the periodic table is actually divided into 4 blocks. These first 2 columns are called the S block, and this is kind of why the periodic table is designed the way it is. You want to imagine hydrogen, and just for this purpose only, helium is the only exception for right now. You want to imagine hydrogen and helium both here when you're doing electron configurations. This is just basically telling you you can hold 2 electrons. It's 2 columns wide. After you fill in the 2 S's, you fill in the 2 P's. Once you've filled in the 2 P's, you fill in the 3 S's. After the 3 S's, the 3 P's. And then it skips. 4S, same order as the periodic table, 3 D's, 4 P's. Okay. And it gets a little tricky down here because it's saying we go from 6S to 4F. Then back to 5D because look at the numbers, 70, 71. Then back to 6P. So remember, these elements technically belong here, but we just don't have space. So we draw them down there. So that's going to be really useful for figuring out the order that they fill. Another way that you can do it is to use this diagram, where what you do is you draw this like on graph paper. So each of these has to be equally spaced apart from each other, both up, down, left, right. So you list your S's here, your P's here, your D's here. And these are all ones that don't exist for an atom that we, these are only theoretically full at any point in time. But this cool diagram would also tell you how to fill it. 1S, then 2S, then 2P, 3S, 2P, 3P, 4S, 3D, 4P, 5S. I recommend not using this diagram, though. I recommend instead just using the periodic table, since you're given a periodic table. So you'll notice something cool about the periodic table then. This column is too wide because S block can hold up to 2 electrons. This block is 6 elements wide, can hold up to 6 electrons. 10 electrons wide because the D's can hold up to 10 electrons. 14 elements wide because the F's can hold up to 14. Okay. So let's figure out the electron configurations for each of these. I'm going to open up a separate periodic table here. Just 1 second. I need another periodic table because we need that when we're going to want to go through these. Let's make it easier. Oh, that's not what I wanted. Let me rotate that real quick. Okay. Right. And I'm going to bring my notes up here. So we want to do the electron configurations here. So beryllium. Beryllium is element 4. What block is it in? S, P, D, or F?
S.
S, that means it's going to end in S. And in fact, it's going to end in 2s2, because this would be the two S's. It's the S's in the second row, and it's the second element over. So the electron configuration here is going to be, first you fill the 1s's. The 1s, 2. Then you fill the 2s's. 2s. And then if you add these numbers together, 2 plus 2, that's 4 electrons. Beryllium has 4 electrons, so that works. Nitrogen has 7. So we start the same way. 1s2, 2s2, just like we did to get to beryllium. But we now need to add 3 more electrons. Since it's in the p block and it's on the second row, it's going to go into the 2p's. Okay, 2p1, 2, 3. 2p3 is the third column. 2p. Would you try sodium on your own, please? Just a moment. Try sodium. Okay, all together starts with 1s, 2, 2s, 2. Sodium is here, it's number 11. So then we have to get through all the 2 p's. So we filled the 2 p's, so it's 2p6.
6.
Good. And now that's full. So then we go to, we're on the third row now for sodium. 3s.
1.
Now vanadium starts getting tricky because vanadium's in the D block. Now remember, the S's and the P's correspond to their row numbers in that this is 1s, this is 2s, 2p, this is the third period, so this is 3s, 3p, fourth period, 4s, but the D's, remember, are one behind. This isn't 4D, this is 3D. This isn't 5D, it's 4D. Remember, I showed you that on this diagram. They're a little bit behind the other elements. So the D's are always lagging one behind. 4s, 3d, 5s, 4d. And the F's are always lagging 2 rows behind. So 6s, and then after 6s, you would go to 4f, then 5d. Actually, it's even more complicated than that. You go 6s, you put 1 electron in 4d, and then say, oh, I'll come back to you later, and then jump to the 4f's. Literally just jumps. It's complicated. And it's not something that I'm going to worry too much about. I'm mostly interested in electrons in the sp and d block. our atoms with those. Okay, so vanadium, same beginning, 1s2. 2s has 2 electrons. 2p is full, it has 6 electrons. Good. Now the 3s's are full, so how many electrons? 3s always has
2.
up to 2. Yeah, s's have up to 2. Then we have here, this is 3p,
6.
which would have
6.
6. Good. And following the periodic table until we get to vanadium. 4s has
2.
and then 3d. So these are backwards, so 3d, 1, 2, 3.
3.
Yep. And then iodine, for right now, let's not write iodine. But what's it going to end in? That's what I'd like to know, is what's the last thing for iodine?
And that P.
It's going to end in, so it's in the 5th row, right? 1, 2, 3, 4, 5. So it'll end in 5, P5. 5P5 is what iodine ends in. So I'll come back to that in just a second. So some important things that you start noticing is anything here in the first column ends in 1. These things all end in S1. These things all end in S2. These all end in P1. These all end in P2, P3, etc. Now there is a shortcut notation. And I strongly, strongly encourage you to use it. Okay? The shortcut notation works like this. For a given element, you find it on the periodic table, then go backwards until you find a noble gas. Remember, these are the noble gases. So you say, well, vanadium, its last noble gas was argon. So you just say argon in square brackets, and this means the electron configuration of argon. It means you don't have to write any of this out. So this is 1s2, 2s2, 2p6, 3s2, 4, 3p6. It's all that stuff right there, and you don't have to worry about it. And then you start as if you were just done with argon. So after argon, you go 4s2, 3, 3. I strongly prefer that notation because, as we're going to find out, we're only going to really be interested in the ends of these things. The ends are the important parts, not any at the beginning. Okay. So let's do iodine in shorthand notation. Shortcut. So iodine, what's the last noble gas that we saw? It was
Xenon.
no, krypton, right? Iodine is here. We haven't got to xenon yet, so it's krypton. And so then after krypton, we would have 5s.
2.
2. Then these are Ds. Remember, these were 3 Ds, so these are the 4 Ds. 4D. 10. And then 5p.
5.
75. Very good. What would antimony be? Antimony is which symbol?
SB.
SB, good. It's only 2 less than iodine, so it's going to be the same thing as iodine except what?
5p3.
Yeah, exactly. 5p3. Same as iodine, but just 2 less electrons. Let's change that to 5 to 5p. So this takes a bit of practice. This is very confusing at first, but once you've done it quite a bit, it becomes pretty easy. Okay. As I was mentioning a moment ago, there is a strong correlation with groups. So, and this is going to be vitally important for figuring out how some of the chemicals behave. All alkali metals, for example, end in S1, right? If we look at the group 1 elements, lithium ends in 2s1, sodium ends in 3s1, potassium 4s1. They all end in s1. This is going to be very important because in the next chapter we're going to see that what these metals all want to do is lose their 1 electron there, that last electron. They always want to lose that last electron. So they're going to be 1 plus charge. So that's going to be critical for understanding how these elements react. There's a lot of commonality because of those electron configurations. Because remember, bonding all is going to be about the electrons, so that's important. All the halogens end in P5. All the noble gases end in P6 except helium. Helium is the only exception for a lot of these things. It ends in 1s2. It's 1s2, that's all. Do all elements follow these rules? No, they don't, unfortunately. So what would you predict the electron configuration to be of copper? What would you predict copper to be? That over a bit more, sorry.
Ten with 3d9.
Yeah, so going backwards, the last noble gas was argon, right? So it should be argon. And then 4s,
2.
2, 3d,
9.
9. But the actual electron configuration is argon 4s1, 10. So there's a number of potholes in here that don't work. All the elements work up to vanadium. And then chromium doesn't quite work, copper doesn't quite work. All the S's and all the P's work. They all work fine. But there's lots of little holes in here. And same thing down here. It makes no sense at all to memorize all the weird ones. I don't have them all memorized. There's just no point to it. So your focus in this class needs to be on the general trend, not on all the exceptions. We'll worry about why those are exceptions in Chem 130. Okay? But for right now, you want to focus on what would you predict it to be. And that's what I will largely ask on the exam is, what do you predict it to be? Okay? Even if it's not the correct one, what do you predict it to be? So silver, for example, you would predict it to be krypton 5s2 4d9. It's not, but that's what you would expect based on these rules. Okay. And then, but why does it do this? The overall reason, remember, is you fill the electrons in order from lowest energy to highest energy. And it turns out that 4s and 3d are very, very close in energy. And so it just is less energy if you push this electron from 4s to 3d. The actual reason is because half-filled shells and half-filled subshells and completely filled subshells are more stable. So this one is totally full, and it's not quite full. But in this configuration, this one's half full, this one's completely full. And so that's why we think that's more stable. The calculations basically tell us so. So lots of little exceptions.
So does that mean the predictive is wrong and the actual?
Yeah, as you get lower and lower, the predictions start getting wrong many times. Okay? In fact, most of these that are predicted are wrong. Okay? The elements I expect you to be able to do are pretty much 1 through 83, except for, or actually probably 1 through 86, except for any of these in the F block. And except for any exceptions. So I don't want you memorizing any exceptions. There's no point in memorizing exceptions. Okay? So if I asked you molybdenum, you'd say, okay, my rules are krypton is where I start, and then I'd go krypton, 5s2, 4d, 1, 2, 3, 4, 44. And whether that's the actual or value or not, I don't really care for right now. So we can always look it up later if we need to know the actual one. But that's your best prediction. Okay. So as I said again, this is going to tell us a lot about how the element is going to behave. It's very, very useful for telling us how many electrons it's going to want to gain or lose in reactions. It's impossible to overestimate the importance of that. And there'll be an even simpler way, as we'll find out as we get a little bit further. Spin. An orbital can hold how many electrons again? Hold up to 2. Okay. But there's a rule with this. It turns out, remember how I said electrons are like particles, but they're also like waves? They have this property called spin. Now, the easiest way to think about this, and it's an analogy, it's not perfectly true, but is to imagine a ball or a globe on an axis. Think of a globe on an axis. You can spin it towards you, which would be like clockwise if you're looking above it, or you could spin it away from you, which would look like counterclockwise. So electrons can spin one way, or they can spin the other way. Now, there's all these terminologies we could pick: spin on, spin off, spin left, spin right. What we call them is spin up and spin down. And it turns out that if you're ever going to pair electrons together in the same orbital, they have to have opposite spin. Okay? So 2 electrons in the same orbital must have opposite spins. I don't think that the textbook brings that up, but I want you to know that. It's called the Pauli exclusion principle. It's a simplified version of the Pauli exclusion principle. You'll learn the more complicated version of it next semester. Let me double check and see if that's in the book. Yeah. Pauli exclusion principle. Should be. Maybe not. Anyway. Yeah, I think he leaves it out. There it is. All the exclusion principle. All right. In section 9.6. Now we're going to represent these spins by little arrows pointing up or down. So an arrow pointing up is going to be spin up, an arrow pointing down will be spin down. Okay. So we can represent this with an orbital diagram, and I'll deal with that in just a second. And then there's another important principle called Hund's rule. And Hund's rule says that if you have electrons that are filling the same subshell, each one has to get one electron before you start pairing them up. So, like hotel rooms, everybody gets their own room until you run out of rooms, and then you start pairing up. Okay. So, for example, remember this? This was my 2p subshell. This was an orbital, this was an orbital, and this was an orbital. The first electron, it doesn't matter which one of these it goes into. Let's say it goes into px. The second electron will not go into px. The second electron wants its own room. So if there's an electron in px, the next electron has to go in y or z. Let's put it in y. So now we have an electron in x and an electron in y. The third electron must then go into where? Z. Everyone wants their own room. When you get to 4 electrons, then they have to start pairing up. So you'll have to pair up, say, x. 5th electron, you pair up, say, y. And then last one, you pair up z. Okay? And their beds have to be pointing in opposite directions. Spin up and spin down. So we're going to represent this with orbital diagrams. It's just a graphical way of doing electron configurations, except it lets us show the spins. So we show up arrows for spin up and down arrows for spin 9. There's 2 ways of doing this. There's your book way. And in the book's way of doing it, you draw squares to represent orbitals and arrows to represent electrons. So an arrow up means spin up, and an arrow down means spin down. So if this is 1s2, 2s1, that's lithium. 1s2, so we'd have 2 electrons, 1 up, 1 down. 2s1, 1 up. We always fill the first one up. In reality, it could be down, we don't care. But by convention, we're just always going to write up. 1s2, 2s2, 2 electrons here, 2 electrons here. Now this is where we see a Hund's rule. Hund's rule says that when you go from 1 electron to 2 electrons, you don't pair them up, you spread them out. When you add a 3rd electron, you spread them out. Each one gets their own orbital. All right, so one more time, squares represent orbitals. What does a group of squares represent? What term?
A shell?
Not quite, very close.
Subshell?
A subshell. That's subshell. This is a subshell. What would be the shell? It would be 2s and 2p. The ones that have the same number in the front. Okay, so this would be a shell. But this would be a subshell, and this would be a subshell. I find these a little bit harder to draw out. They look nice and professional on textbooks, but they're not economical for space. The way I prefer to do this is this way, which is from down up. And so instead of using boxes, I just use lines. And this is more common. And in Chem 130, you're going to be doing it this way for a lot of different diagrams, so it's important. By the way, it doesn't matter if you draw the arrows as half arrows or whole arrows. You can draw half arrows or whole arrows. Just be consistent. Either way means the same thing. It's just easier on a computer. computer to draw whole arrows. That's why they drew it. So the only thing that's important is the directions, up and down. Okay, so let's do this, for example, for titanium. And there isn't really a shortcut notation for this. We could make one up, but let's just do this. So titanium is 1s2, 2s2, 2p6, 3s2, 6, or s2, so I'm going to have 1s. 1s has how many lines always? 1. 1s always has one orbital. 2s, 1, 2p. P's always come in sets of 3 orbitals. 3s, s is always come in sets of 1.
2.
Yeah, 2 electrons, but 1 orbital. Okay. 3p, always come in sets of 3 orbitals. After 3p, we have 4s. This is again always come in sets of 1 orbital. And then 3d, how many on 3d? How many lines should I have for d's? These come in sets of
5.
5. Good. All the bottom ones are full of electrons. So 1s has 2, so spin up, spin down. 2s has 2 electrons, spin up, spin down. 2p would fill these electrons one by one, up, up, down, down, down. 3s has 2 electrons. Down. 3p has 6 electrons. Spin up, spin up, spin down, down. 4s has spin up, spin down. And then 3d2, 2 electrons, so spin up. Sometimes I ask on exams, I'll draw one wrong and say, what did I do wrong? You know, you always have to go from bottom to up. That's the Aufbau Principle. Lowest energy to highest energy. The spins always have to be opposite if they're in the same orbital. That's the Pauli exclusion principle. You can't have 2 ups in the same one. And you always have to, you can't pair them up until each one of these has 1 electron on a given level. That's Hund's rule. Now, what is S2 minus? Sulfur, if we look at it on the periodic table, I will use a shortcut notation for this one. So let me just say neon. I'm saying I can't use shortcut notation. I'll put neon at the bottom. And then sulfur would be what? Sulfur would be S2. 3p4. But this is sulfide. It has 2 more electrons. So if I have to add 2 electrons, they're going to go where?
3p6.
Yeah, it'll be 3p6. I can have 2 electrons there. It'll be 3p. So all as I said, I'll just start from beyond. So 3s. S's always have 1. 3p's 3 orbitals. 1. Okay, so that's what this is all called electronic structure. It's knowing where the electrons fill into atoms. So we can understand how they're going to react. I will talk on Thursday about the next concept, which is periodic trends. Periodic trends is basically being able to look at the periodic table and say, there's a certain property, like how big an atom is, its radius. And we will see that the radius of an atom generally gets bigger as you move from the top of the periodic table to the bottom. On the other hand, as you move from the left to the right, an atom generally gets smaller. So we're going to be able to see that the periodic table tells us about a lot of properties pretty well. So that's why it's kind of a brilliant invention the way it's designed, because it's telling us electron configurations, it's telling us about properties of atoms. It's not just, a bunch of symbols. If we just wanted a bunch of symbols, we would have found a different way to put them together that would be easier and nicer looking. This tells us massive amounts of information. Okay. The lab this week is a fairly easy one. Oh, let me just really quickly talk about the labs. I have not graded last week's labs. I'm going to allow one resubmission on some of those. Only one this time. And then this lab, I don't think I'm going to allow any. Obviously, the due date would have been Sunday, so I'm going to have to extend that because I wanted to get the exams graded. That was more important this last time. So we'll go ahead and we will talk about the labs today. I will, during lab, I'll probably be grading last week's lab. So I'll hopefully get those to you sometime soon. So if you need to make changes, you can make changes. But the big things that I would say about the lab report still is the same thing I would say about the exams. Read, 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 read. Significant digits, significant digits, significant digits. Over and over and over and over and over again. I'd say those things. Read to the right decimal place. I can't keep saying that anymore. That was the point of exam 1. A lot of it was to make sure you got those skills down.